Sorry? Yeah, I'll use that one.
All right, our next talk will be from Nathan Bowler. He will be talking about piecing together quasi-graphic matroids from graphic pieces. Sounds interesting.
Yeah, thank you. So I wanted to, before I get going, I wanted to say, first of all, thank you to the organizers. This has been a really great workshop. It's been great to meet up with some people that I already knew and with some people that I didn't know and talk about lots of interesting things and to see how the different parts of Matroid theory, which maybe had been going in different directions, are interacting a little bit. So yeah, this has been it's been really good. So I'm very happy to have a chance to also talk here. I'm going to be talking about some joint work with James, who just spoke, with Daryl Funk, who's not here, and Jim Gielan and Peter Nelson, who are both at the workshop. And I'm going to be talking about piecing together quasi-graphic matroids from graphic pieces. So I guess I should start by saying a little bit about what these quasi-graphic matroids are. And they're a generalization of the frame matroids that James was talking about in his talk. So let me go over that definition again, just because the notation for quasi-graphic matroids will be very similar to the notation for frame matroids. So I'll try to keep this quick. You probably remember a biased graph is a graph together with a partition of the cycles into two different kinds of cycles, balanced cycles and unbalanced cycles. And the rule was that if you have two vertices and three disjoint paths between them, then that gives you three cycles in that configuration. And you're not allowed to have exactly two of those cycles be balanced and the other one be unbalanced. Right. And such a configuration of three paths I'll call generally a theta. Okay, so here are the frame matroids that James defined. The circuits are given by taking some biased graph, in the sense I just said, and taking the circuits to be the edge sets of either balanced cycles, thetas in which every cycle is unbalanced, so unbalanced thetas, unions of two unbalanced cycles that have exactly one vertex in common, so those are tight handcuffs, or unions of two disjoint unbalanced cycles together with a path between them. Right? Those are loose handcuffs. Okay, now, as Rutger mentioned in his question, there's a closely related class of matroids called the lift matroids, where the definition looks almost the same unless you look very, very closely. So again, a lift matroid is given in terms of a biased graph. And the circuits are almost exactly the same thing. So we still have the balanced cycles, the unbalanced thetas, the unbalanced tight handcuffs. But instead of these unbalanced loose handcuffs, what you take as circuits is edge sets of unions of two disjoint unbalanced cycles. Okay. And in either of these cases, I mean, maybe you have to go away and calculate a bit, but in either of these cases, you do get a matroid. These are both important classes of matroids studied by Zaslavsky, historically important and structurally important. And there are two sort of very basic questions that we can ask about a class of matroids like this. The first is something that James mentioned in his talk, or almost mentioned in his talk, which is recognizability. Is there a polynomial time algorithm given a matroid in this class, or given a rank oracle for a matroid in this class, to recognize, given a matroid, to recognize whether or not it's in this class? Right? That's the recognizability question. And then, does this class have finitely many excluded minors? And unfortunately, the answer for both of these classes of matroids, for frame matroids and for lift matroids, and for both of these kinds of questions, is no. And this was shown by Chen and Whittle. And roughly the way that they showed it is that they built sort of largish matroids. Let's do this for the frame matroids first of all. So largish matroids which are almost frame. So they almost look like they're defined like this, except that just hidden away you have maybe one or two circuits which are of this type instead. Right? And now if you want to know, is this really a frame matroid, you have to check all the places where those one or two slightly different circuits might be. That's exponentially much stuff that you have to check. And so you can't tell that whether or not this is really a frame matroid. And also these guys give you matroids which are very close to being frame, and so this gives you also infinite classes of excluded minors. The same is true on the lift side. You can build matroids which are very, very close to being lift. They almost look like this, except that they have just one or two hidden circuits of this kind, right? And so you can't tell, okay, is it really a lift matroid? So if we want to clean this up a little bit, if we want to get a good class of matroids which sort of interpolates between these two and covers both of these classes, then one natural idea, and this is due to Gielen, Herrads, and Whittle, they introduce a class of quasi-graphic matroids in which you say, well, we'll just allow still these three kinds of circuits, and sometimes allow this kind of circuit, and sometimes allow this kind of circuit. So this gives you the class of quasi-graphic matroids. So, just as those two classes were defined in terms of biased graphs, we need a just very, very slightly more complicated structure to define quasi-graphic matroids. We need proper tripartitions. So we still need some collection of balanced cycles in our graph, but now we want to partition the remaining cycles up into two kinds of cycles, frame cycles and lift cycles. And the frame cycles are hoping to participate in circuits of this kind, whereas the lift cycles are hoping to participate in circuits of this kind. Okay. And the rules are also almost the same as before. So we've still got this rule here, which says that you can't have a theta in which exactly two of the cycles are balanced and the other one is unbalanced. And then we have a new rule, which says you can't have two disjoint cycles in your graph, one of which is frame and the other of which is lift. Why not? Because then these two cycles would fight each other, right? I mean, the frame one says, oh, no, if we want a circuit, we should include a path between us, whereas the lift one says, no, just our union should already give us a circuit, right? So to avoid this kind of confusion, we forbid this possibility of having two disjoint cycles, one of which is frame and one of which is lift. Okay, now this is a very simple condition, but you might think this is a very restrictive condition, right? To say that every frame cycle has to meet every lift cycle, maybe there's just not many options for how you can organize for that to happen. But in fact, it's not super restrictive. You can get large, interesting classes of matroids with such partitions. For example, if I take a torus, and I have a graph embedded in the surface of this torus, then I could take each of the contractible cycles to be balanced, and if I look at the remaining cycles, maybe I have a cycle which goes around here, like this, and now if I take a cycle of a different topological type, maybe one which goes around the torus this way, then they will always have to meet in some point, right? So for the non-contractible cycles, I can just divide up, I can choose for each homotopy type of cycles whether all cycles of that type should be frame or should be lift, and I can make all of those choices completely arbitrarily, and I'll always get a proper tripartition like this. Okay, so I promised now to give you a definition of quasi-graphic matroids. And if I have such a proper tripartition, well, I guess you've worked it out by now, that the circuits are just going to be given by similar things to before, the balanced cycles, the unbalanced thetas, the unbalanced tight handcuffs, and the loose handcuffs in which both cycles are frame cycles, and then just disjoint unions, unions of two disjoint lift cycles. Okay, so if you take the edge sets of those kinds of configurations, you'll get the circuits of a matroid. There's a little bit of checking that you have to do to see that. There's a small technical point here, which is that you should take this thing that I said you should close this under direct sums, because the class as I just defined it is not closed under direct sums. And if you do that, then you get the class of quasi-graphic matroids. So this wasn't the original definition of Gielen, Herraz, and Whittle. They defined them like this. And this definition, I wanted to explain it because sometimes it's easier to use this definition if you're computing with quasi-graphic matroids, even if they're then harder to visualize. So again, we're going to have a graph which our quasi-graphic matroid is defined in terms of. It's the same graph as in the definition on the right, and it's called a framework for the quasi-graphic matroid. Remember this name, this will be important later. Okay, so our graph is called a framework for a quasi-graphic matroid if, first of all, its set of elements is just the edge set of the graph. Secondly, the rank of any component of the graph is at most the number of vertices of that component of the graph. Thirdly, okay, what does this third rule say? It says if I take a vertex of the graph and I look at the edges going out of it, and then I look at all the other edges of the graph, so I'm taking this outer set of edges, and I'm going to take the closure in the matroid, then I don't pick up any of these edges going out of this vertex except maybe loops. So in the closure, I'm going to have still all of this stuff and maybe some loops at this vertex, but nothing else. And then there's a final condition. I mean, yeah, it's not too hard to check all of these conditions in the definition that I have there on the right, that if you have a circuit, then the graph induced on it has at most two components. It's a slightly fiddly condition, and if the matroid is sufficiently connected, you don't need to worry about it. Okay, good. So, right. So we still have these questions from before that we were asking about frame matroids and about lift matroids. Are they recognizable? Are there finitely many excluded minors? And of course, we would hope that the answers to these questions for quasi-graphic matroids would be yes, but you've probably noticed on my slide, instead I have two big fat question marks here, because we still don't know, even after quite a few years, even whether this class of matroids is recognizable. And so we're working hard on that. We have some good ideas. And we expect, I'll just go back. We expect also that there will be finitely many excluded minors, but that's probably quite a lot harder. But I want to talk about some of the problems that come up when you look at these kinds of questions, and one tool that is helpful for attacking some of those problems. So the first problem, this is something James already talked about a bit, is that it's possible to have two different frameworks for the same quasi-graphic matroid. And the graphs can look really very different to each other. And this is a problem if you're sort of looking at recognizability. Maybe you want to keep track of the various different frameworks you have for different quasi-graphic matroids as you go along, but maybe sometimes there'll be exponentially many possibilities, or it'll be some very complicated options. And you can have some weird-looking options, like these ones that I've drawn here. So for this left-hand picture, for example, this is a way to This is a picture of a way to build two different frameworks for the same quasi-graphic matroid. So bear with me a moment. What do? You take an icosahedron embedded into a sphere. And you identify each point of the sphere with the opposite point of the sphere. So this is going to give you a projective plane. And because the icosahedron is symmetric, right, it's just going to collapse down, and it'll give you an embedding of K6 into the projective plane. And here in this picture, I've taken this embedding of the K6, and for each face, for each triangle, I've stuck in a little triangular piece. So what does this mean? For each of these, how many are there? So 20 divided by 2. For each of these 10 faces that are left, I take some graph and some 3 marked vertices of that graph, right? And then I just stick all of those graphs together according to this scheme, right? So here are my 3 marked vertices in this graph, but I just keep on sticking them all together, and that'll build me some big graph. But now there's another way that I could have stuck together those same graphs, which I've also indicated in this picture. Let me see. I sort of pull them apart, and now I take all of these purple marked corners, and I stick those all together at one vertex. And I take all of the orange corners and stick those all together at some vertex, and all of the red ones at another vertex, and so on for each color. And you end up with a picture which looks kind of like the picture you started with, but like very crazily rearranged. And this will give you a different framework, as it turns out, or these 2 graphs will both be frameworks for the same quasi-graphic matroid. Okay. Here we have another such scheme with 4 graphs, each with 4 marked vertices and somehow stuck together in a torus. Here we have another slightly weirder looking scheme embedded in a cylinder. And James had some other examples embedded, for example, in a Möbius strip, or he had these twisted flips. There are a lot of different ways to do this, and we want to understand this kind of structure and what's going on in there. Okay. Yes? Oh, sorry. Should I put it higher up? Yeah, okay. Sorry about that. Okay, so... So I'm kind of gathering a menagerie of such examples. So if anybody has a favorite example of such a thing, then please come and talk to me about it. I want to know all the examples like this that people know about. Okay, so another issue that can come up, or that's important for recognizability, is that it's good to make your matroid as connected as you possibly can at the start. So if you have maybe some 3 separations, then you want to just reduce to smaller matroids or even solve the whole problem. And this is an example of one particular kind of 3 separation, which you could have. You could have 2 balanced subgraphs stuck together along a 4 separation of the original graph. Now that graphic 4 separation turns into a 3 separation of your quasi-graphic matroid. And in these circumstances, it would be nice if you could just compute and work out what these balanced pieces should look like. Okay, so what is a framework for dealing with these things? Well, we need some structure which says how we're going to stick together all these sort of graphical pieces. And what we need is really a hypergraph. So a jigsaw puzzle, that's the structure we're working with, is going to be given, well, I suppose by a multi-hypergraph. We're going to want to allow parallel edges. But it's going to be, we're going to have some vertices and then some edges of the hypergraph. Here I've drawn a hypergraph with 6 vertices and 4 edges. And for each such edge of the hypergraph, we're going to want to stick in some sort of graphic type piece. And so we have some extra information. For each edge of the hypergraph, we have a set of edges of our matroid, which should be the edges of the graph that we stick in at that position. So we have a partition of the edges of the matroid into various sets, which assigned to each edge of the matroid one of the edges of the hypergraph, where we want to put it. And the tool that we have for this is that under these circumstances, we can work out what these graphs should be. So we can find what's called a solution to a jigsaw puzzle. So a solution to a jigsaw puzzle just gives you a framework for the matroid, which consists of graphs stuck together according to the scheme of that hypergraph. Right? So you have that the vertices of the hypergraph are a subset of the set of vertices of the graph. And for each edge of the hypergraph, you have a subgraph of your graph, and these should be balanced in the framework, meaning all their cycles are balanced. And they shouldn't overlap with each other except in these vertices of the hypergraph. Okay, and each of the subgraphs should contain the correct vertices from the hypergraph. And what we showed is that if you're given a jigsaw puzzle on a matroid, you don't have to know that the matroid is quasi-graphic yet, then there's a polynomial time algorithm. Okay, so given it should be a 3-connected matroid, and a jigsaw puzzle for that matroid will determine in polynomial time whether that jigsaw puzzle has a solution. And if it does have a solution, then it will find one for you. Okay. And by finding one, it will in particular show you that this is a quasi-graphic matroid and give you a framework for it. Now, you might wonder, why find just one? Why not find them all? But the problem is there will, in some cases, be exponentially many possible solutions to a jigsaw puzzle. And so there's no hope of a polynomial time algorithm to find them all, but this is what we could hope for, something which tells you whether there's a solution, and if so, finds one. Right, and I think I'll stop there. So thank you.
Thank you, Nathan. Does anyone have any questions for Nathan?
So the matroid is given by oracle, an independence oracle, or?
Yeah, the matroid is given by a rank oracle.
Any other questions? Oh, thanks, Charles.
Sorry?
Can you do a listing algorithm?
Right. Okay, and you keep going, and always in polynomial time you get a next one. Hold on. Yes. I'm pretty sure you could. I will look at the algorithm in detail and tell you for sure later, but I'm pretty sure the answer is yes.
All right. Does anyone have any other questions? If not, let's thank Nathan again.